Hello everyone, welcome to third session of this crash course series. Today we are going to analyze the paper of thermodynamics and thermochemistry. Before that, in this session we are going to cover the weightage of the concepts, revision of the entire chapter and important formulas we are going to analyze. I know I missed chemical bonding and periodic properties chapter. So I'm going to attach those two formula sheet and practice questions in the description of this video. So please do check it out if you want to practice those questions as well, because those chapters also having the importance in JEE Main and Advanced. Those two are the foundational chapters for other chapters, right? Okay, without any further delay, let's analyze the previous year question papers to get an idea what is the weightage of the concept about thermodynamics and thermochemistry. If I'm taking JEE Main, average questions per year is 3 to 4 and you can expect easily 12 to 16 marks from this chapter alone. That much important this chapter is. Okay, so please be careful with the numericals asked in this chapter, because that gives you free marks, that gives you easy marks. The question type distribution, mostly they will be asking the numericals and MCQs. Both the questions will be mostly asked in the numerical part, like the problem solving skills. Sometimes they'll ask the theoretical stuffs as well, like intensive properties, extensive properties, internal energy, state function, path function, and etc. In case of JEE Advanced, the average questions per year is 2 to 3 again, and the mark weightage is 8 to 12 marks out of 66, guys. So please be thorough with this chapter of physical chemistry. Question type, as I said, integer, multiple choice question, and matrices match also. Talking about the concept of this chapter includes first law of thermodynamics, where we talk about internal energy, heat capacity relationships. Those formulas we are going to give, we are going to revise. I'm just telling you the concepts. And talking about thermochemistry, Hessler application, Born-Haber cycle, importantly, enthalpy calculations, which is very important. And you can't find a paper without asking entropy or enthalpy or free energies. The equally important, those are the internal energies or isothermal expansion, reversible, adiabatic expansion, compression, and everything. And least weightage goes to heat capacity and Kirchhoff's law. Kirchhoff's law mostly they won't be asking for JEE Main and Advanced, because they will be covering those in physics. Okay, so for chemistry we stick with heat capacity only. So now what we are going to do, we are going to revise the chapter. I'm just going to brush up your knowledge. I'm not going into deeper. If you want any deeper concepts, if you want to discuss any concept in detail, please be informed, like please let me know. I'll be doing that for you. Okay, so let's brush up the concept we have already. It starts with type of system. I'm not going into the fundamental terminologies like what is system, what is surrounding and everything. I hope you guys already know about that. Okay, so let's get started with these concepts of type of system. There are three types of system: isolated, closed, and open system. Isolated, we know, no heat energy, no exchange of heat energy or any kind of energy with the surrounding. For example, you can take a vacuum flask. Okay, Closed system, you can take an example of glass of hot water kept closed. Okay. And for open system, you can keep the glass of hot water opened. Right? So let's move on to the key properties. The questions can be asked from here. Which are all the following are intensive properties? Which are all the following are not intensive properties? This kind of question you can expect from this part: intensive property, extensive property, state function and path function. These are very simple concept. This will give you free marks. Please note it down. It is as simple as that. You can remember it like it starts with the letter IN, so it is independent of the quantity. For example, temperature, pressure or viscosity. You can remember it like, what is the temperature of your surrounding? It will not change depending on the quantity, right? If you are taking 100 degrees Celsius, one glass of water, that remains the same as if you are taking 1 liter of water also. So these properties will not change with respect to the quantity. They are intensive properties. Okay. Talking about extensive, it's just opposite. It depends on the quantity, mass, volume, entropy. These are some famous or most asked examples I just picked out for you. So please note down these examples as well. Talking about the next part, that is state and path functions. State function is depend only on initial and final state. It just depend on from where you are arriving, where you are starting and where you reach. It's about the destination and your place. It's not talking about whether you are going by train, whether you are taking the bus route or whether you are going by walk. It does not depend on that. Okay, that is state function. Okay, then path function, which is, it depends on the path followed. By the name indicates, most of the scientific terminologies you can get it from their name. Okay, so please be careful with the name itself. The path functions are the values depend on the path followed. You can try out some examples. I'll be attaching those things in the formula sheet itself, so don't worry. Then let's move on to the laws of thermodynamics, which is also super important. The first law, which is talking about neither be created nor be destroyed and blah 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 things. What we have to know about from the first law is this formula. Delta E equal to Q plus W. What is E? E is energy, internal energy you can take, but we are not talking about the internal energy in the first law. Q, heat. W, work done. Okay, here the point to be noted is work done on the system means the W value becomes positive if the system is work done is on the system. System is not doing work, it's the work is done on the system. If the work is done by the system, then W is negative. Okay, similarly, if the heat is observed, obviously the Q value becomes positive, and the heat is released, the Q value becomes negative. I know most of the students do the mistake over here. work done on the system or by the system. You can remember it like work done by the system. Let's say the man is doing the work. What will happen? The energy will get decrease, right? He will be losing the energy. I'm telling this for an example, okay? Don't take it that it's serious, like her energy will also change. No, it's not like that, mostly. But work done by the system, if a man is doing work, obviously that will be minus, right? So the W will be negative value. What about the second law? Second law is talking about heat cannot be completely converted to work. You can't build a machine which can do the work with 100% the energy you have provided. It will consume some commission into it, right? So the heat cannot be completely converted to work without compensation. Every man needs some commission to do the work, needs some other way of commission to do the work, isn't it? So that is second law states about. Guys, you just relate the science with your daily life so that it will be stick in your mind for a longer period of time. Okay, so please be careful. And moving on, from the second law, we are talking about the spontaneous process and non-spontaneous process. What is spontaneous process? The spontaneous processes are which happens spontaneously, like which happens naturally, right? So let's say after some days they will get rotten. The fruit will like overripe. Those are spontaneous processes. Non-spontaneous processes are just opposite. Okay, the whole universe is moving towards the spontaneous process. In that case, the delta G must be negative. The third law of thermodynamics, it is talking about entropy of perfectly crystalline solids approaches zero at absolute zero. It approaches zero. Please be careful with the term. It approaches zero at absolute zero. Absolute zero of what? Temperature. At absolute zero temperature, the entropy of perfectly crystalline solid approaches zero. Okay, what is entropy, by the way? Entropy is like, it's randomness. How we are. It's random people, isn't it? So it talks about the randomness. Entropy is nothing but the randomness. Entropy of the perfectly crystalline solid approaches zero at absolute zero. The formula to be noted here is, let's say I'm taking it in limits. Temperature when it reaches 0 Kelvin, okay, entropy will also reach 0. This is the limit. I forgot to mention the second law formula, which is talking about entropy and free energies, right? Entropy delta S, which is equal to Q reversible by T. Q, once again, that is heat. T is temperature. There is a huge difference between heat and temperature, dears. Okay, so the entropy change, which is equal to Q reversible by T. Entropy, as I told you, which indicates the randomness. The question can be asked in this way: arrange the following in case of entropies: solid, liquid and gases. Which is having lot of entropy? Yes, that is gases. Gas followed by liquid and followed by solid. And you know why? Because the molecules of gas particles can move freely, there is no restriction, so it is randomly distributed. And followed by liquid, it's as comparatively much more freely movable, and then comes solid. Okay, entropy is always denoted by the symbol small s. Okay, so now it's time to talk about the free energy. What is free energy? It's a maximum amount of energy available to the system during the process. How much ever energy we are having to do the process, how much ever energy we are having to sing a song, do a dance movement. So the maximum amount of energy is available to the system during the process, which can be converted to the work, which can be converted to sing a song, which can be converted to do a dance, right? It should be converted to some useful work. That maximum energy is called free energy. It is mentioned by the symbol G, capital G. And mathematically, it is mentioned as G equal to H minus Ts. H refers to enthalpy. What is enthalpy? We will see in a while. T for temperature, S for entropy. Up to this point, I hope this is clear. Let's move on to important processes. The first process now I am going to talk, that is isobaric process. Bar, what is that unit is mentioned for? Pressure, is it? Iso means same, bar which is for pressure, so pressure same. Same means delta P which is equal to 0, which means that the pressure is maintained constant. So in that case, what will happen to work done? So the work done becomes minus P delta V. If I am plotting a diagram versus pressure and volume for isobaric process, as I told you, difference between the pressures are same, delta P which is same. So the graph will go like this, isn't it? Only the volume will change, pressure will not. Now let's move on to isochoric process. In this case, isochoric, core you can remember it for volume. Iso means same. So same volume, that means constant volume. In that case, work is not done. So if I am plotting a graph between pressure and volume, I'll be getting it like a steep vertical line, because Tv which is equal to 0. The third process here I am going to talk, that is isothermal process. Iso same, thermal which is temperature. Temperature will not change. That's what it means. So delta T which is equal to 0. So at constant temperature, what will happen? Let's say I am plotting a graph between pressure and volume again. If I am keeping the temperature as constant, So what will happen to pressure and volume? I'll be getting a curve. As the pressure decreases, the volume will increase. Correct? Now, the fourth process, that is adiabatic process, where there is no heat change. Q is equal to 0. In that case, if I'm plotting the same graph, then I'll be getting, if the heat is not changing, then the temperature delta Q, dq, which is equal to 0. Right? So the questions can be asked from graph part as well. So please be aware of PV is equal to nRT and do it accordingly. So now we have covered the four important terminologies: isothermal, isochoric, isobaric and adiabatic. Out of these four, two processes are very important in this chapter because the questions can be asked from that part. First one is isothermal, the second one is adiabatic. We know what is reversible and irreversible process is. Reversible process which can go forward and backward. Once it attained the product, it can go back and reach the reactant. But in case of irreversible product, irreversible reaction or process, it is one-way road. You can't go back, right? And we know about what is compression, what is expansion. Compression means I am applying the pressure and compressing the gases so that the pressure is increasing and the volume is decreasing. Expansion means I am decreasing the pressure so the volume will get increased. That is expansion, and a compression, that is pressure increases, volume decreases. How it is related to isothermal and adiabatic? Let's check it out. These formulas. We had huge derivation for these four situations: isothermal, expansion, reversible and irreversible. Compression of isothermal, compression of reversible and irreversible. What to be noted here is that the formulas, the work done, Q, the question will be asked in that part. Anyway, we are going to solve some questions, but let's go through this formula, which is for reversible isothermal expansion. The work done, where W is equal to minus nRT ln V2 by V1. Please note it down. It goes like both are minus, but still the trick part is here. V2 by V1, and in case of pressure, that is V1 P1 by P2. Okay, if they are asking about heat observed, then Q is equal to minus W. Heat is observed. So the Q is plus and the work done, that is minus. In this case, the maximum work can be obtained, but the process is slow. If I'm talking about irreversible expansion, this formula is important. The questions was asked in past three years of papers. P external into V2 minus V1 for work done. We can expect this less work than the reversible processes, the heat absorbed would be same, Q is equal to minus W. It is rapid and uncontrolled process. But in case of reversible, that is slow. Compression. Isothermal compression, what will happen? The work done by the surrounding on the system, which means that W will be positive, as we discussed before. Work done is positive. So heat released to the surrounding. So Q becomes negative and work done becomes positive. Okay. It is isothermal compression process. Compressing. So work is by surrounding on the system. Okay. By surrounding on the system. Okay. So let's move on to adiabatic expansions. Sometimes the advanced question can be asked from this part. So this is also equally important, the temperature relation, pressure relations and everything. Here the gamma stands for the coefficient. Mostly they will be giving the values of gamma. Don't worry about that. Talking about adiabatic compression, it goes as it is for expansion, but the temperature increases. Yes, the compression happens, work done on the system, so which makes it positive, and the internal energy increases, which was given over here. Then I have told you we are going to talk about enthalpy. Enthalpy, which is nothing but which is related to an energy, right? So the enthalpy is the total heat content of the system at constant pressure. So delta H, which is equal to delta U plus P delta V. U, that is internal energy, plus P delta V, P for pressure, V for volume. In case of exothermic, exo means heat releases, right? Releases, which means that delta H is less than 0, because the heat content in the system, heat content of the system, it's referred to delta H, right? So endothermic, that is heat absorbed in the process, which makes it delta H positive. This is very, very important. And I have told you about entropy. And entropy of the reversible process, delta S plus delta S of system plus surrounding, which becomes 0. This was asked in one of those JEE main paper, I guess if that is 2014. The free energies, we talked about that. Now we came to almost end of the chapter. I just covered what are all the important equations required, and we'll solve the problems so that we'll get an idea. More you solve, more you'll be confident, more you'll know about the chapters, the concepts. Okay. So the important formula for the calculations are 1 joule, which is equal to 4.2, you can take 4.2 into 10 to the power 7 ergs. Sometimes they'll ask the unit conversions along with the numericals, right? Work done, W is equal to F into dx, I mean the work done by the system. Heat capacity of the equation, weight plus mass. Here is this Capron equation which should be asked for JEE Advanced. So now it's time for solving questions of previous year papers. The first question, which was asked in Advanced 2018, I just modified this question. The question is that a system absorbs 400 joules of heat and does 200 joules of work on the surrounding, which means the work is done by the system, right? So calculate change in internal energy of the system, work done on the system, heat released by the system. So first calculate the internal energy of the system. How to find that? The simple formula you can apply: delta U, which is equal to Q plus W. Q is heat and W is for work done, right? So here the point to be noted here is work done is by the system, because it is given on the surrounding, which means that is work done by the system. So by the system means W becomes negative. So I have to take W as minus 200 joules. So Q, which is plus 400 plus minus 200 joules for work done. So in total that becomes plus 200 joules. The second part is work done by the system is how much? On the system is how much? So work done on the system, it will become just opposite, isn't it? So plus 200 joule. Heat released by the system, which is just opposite of the heat absorbed. So this part of the question, these three covers whether you understood the concept of work done thoroughly or not. Okay, so you have to understand what is doing the work, whether the system or the surrounding. Depend on that, you will find it out what is Q, what is W. Okay, now let's move on to the next part, that is for an ideal gas undergoing isothermal expansion from 2 liters to 4 liters at 300 Kelvin. Calculate the entropy change. Given that N is equal to 1 mole. They are asking for isothermal expansion. Okay, so for isothermal expansion, delta S equal to number of moles into R ln V2 by V1, right? They are asking for entropy, just substitute the value. R value, which is 8.314 joule per Kelvin per mole, ln V2, that is 4 liters, and V1 is 2. So it becomes 2 ln 2 into 8.314. So the final answer you'll be getting 5.76 joule per Kelvin. Please note down the formula for entropy. I told you guys, do as many problems you can. You will get an idea how to solve a question. Then let's move on to the next question, that is heat energy operates between 400 Kelvin and 300 Kelvin. Calculate maximum theoretical efficiency As per the second law, we know the system can't convert the 100% of the heat energy to the work. How much we can get it? We found that from the Carnot cycle, right? So Carnot engine formula, that is eta, which is equal to 1 minus T2 by T1. Just substitute the values. 1 minus T2 300 by 400. 1 minus 3 by 4. 3 by 4, that is 0.75. 1 minus 0.75, which is equal to 0.25. They are asking for percentage, then it would be 25%. As simple as that. The second part is asking about work output if heat output is 1000 joules at maximum efficiency. If heat output is 1000 joules. So to find the work output, W, you can use eta, that is efficiency or capacity, into Q. It is 0.25 into 1000. That will give you the work output, how much output we got. Which will become 250 joules. The next question we are going to solve, that is for an adiabatic process. PV raised to the power 1.4, that is gamma value, equal to constant. If initial pressure and volume are 1 atm and 1 liter respectively, what is the final pressure when volume becomes 2 liters? This question is kind of tricky, but if you know the formula, you'll ace it. That's why I'm telling you, for physical chemistry, formula plays an important role. So please memorize or please understand the formula. It's better to understand it. Okay, do as many problems you can. Okay, so talking about this PV gamma, right? So they have given the gamma value as 1.4. Right? So for adiabatic process, we know the formula P1 V1 gamma, which is equal to P2 V2 gamma. Gamma value is given, just substitute the other values. The pressure, the P1 and V1, that is given 1 atm and 1 liter, and the final pressure we have to find V2, which is equal to 2 liters. This substituted over here, 1 into 1 raised to the power 1.4. P2, I don't know, keep it as such. V2, 2 raised to the power 1.4. So P2 becomes 1 by 2 raised to the power 1.4. That becomes 0.379. This type of question, if they are mostly, they'll be asking it in MCQs, because that you can take the closest value. Okay, so from the given options you can take the closest value, because you can find the 2 to the power 1.4. In that case, just do 2 to the power 2 square and find the closest value possible. Now let's move on to the next question. A process has delta H which is equal to 85 kilojoule and delta S that is 250 joule per Kelvin. At what temperature will the process become spontaneous? This is an important and interesting question. At what temperature the process becomes spontaneous? We know that at spontaneity, delta G, free energy, becomes negative. It's less than 0. So delta G relation to delta H and S is that delta H minus T delta S. So delta G, I know that is negative value. So for the sake of problem, I'm going to take that as 0. Delta H, that is 85. It is given in kilojoules. So I have to convert it to joules. Then T, I am going to find it. Delta S, that is 250. So T is equal to 85,000 divided by 250, which will become 340 Kelvin. So at 340 Kelvin, the process becomes spontaneous. This kind of question can be asked in this year JEE Main. Please be careful with this. Please understand the question flow. Now let's move on to the next part, that is calculate the work done in joules when 2 moles of ideal gas expands isothermally and reversibly from 10 liter to 20 liter at 300 Kelvin. Although this is asked in NEET 2019, this is a very interesting question, can be expected to be asked in JEE Main because they have given the values of volume, temperature and N value. They are asking it to calculate the work done. So we know that this is isothermal process and reversible. Whether that is expansion or not, yes it is. 10 liters to 20 liters, obviously that is expansion. So for isothermal expansion, W becomes minus nRT ln V2 divided by V1, right? So I'm going to just substitute the values. Minus 2, R value is 8.314, temperature 300 Kelvin ln 20 by 10. So it becomes ln 2 then substitute the ln value, you will get the answer in negative 3453 joules. Okay, since this is asked in reversible expansion, this can be expected in JEE Main as well. Don't underestimate this kind of questions. Cool. The next question, the entropy change for the reversible process in an isolated system is. This is an old type of JEE advanced question, but still I'm considering it because very interesting one, can be asked in the MCQs as well. For reversible process in an isolated system, what will happen? Delta S of system plus delta S of surrounding becomes 0, right? So since it is isolated, what will happen? delta S, there is no heat exchange, right? Energy exchange. So delta S is 0, S of surrounding becomes 0, and the system will also be 0. Both the delta S becomes 0. The next question is calculate the enthalpy change when 1 mole of water at 373 Kelvin and 1 atm vaporizes. Delta H of vaporization, which is given over here, this is a constant value. What they have given, 1 mole of water at 373 Kelvin. 373 Kelvin is 100 degrees Celsius. So it vaporizes, right? So we have to find the delta H value. I'm telling you, this question is the most simplest question asked in JEE Main and most simplest question in thermodynamics, because they have given all those steps for vaporization. 1 mole, okay, 100 degrees Celsius, 1 atm, that is equal to the delta H vaporization, which is 40.7 kilojoule per mole. The gas expands from 2 liter to 5 liter against the constant external pressure of 1 atm. Calculate the work done by the gas. 2 liter to 5 liter is an expansion at constant external pressure. So delta P becomes 0. P value is 1 atm. Calculate the work done. So the work done becomes minus P delta V minus 1. The volume changes are 5 minus 2, that is 3. So it becomes 3 liter atm, right? Check the units given in the options as well. If they are asking for joules, then you have to convert the liter atm to joules. You will be getting 303.9 joules. Now let's move on to the next question, asking for calculate the change in internal energy when 2 moles of an ideal monatomic gas is heated from 300 Kelvin to 600 Kelvin. Given heat capacity at constant volume, that is CV, 3R/2. We didn't discuss about heat capacity at constant volume and constant pressure, Cp and Cv relationship, but I'm solving this question using the internal energy formula, which will be useful to you, that is delta U Cv delta T. Delta U, that is for internal energy, T for temperature, N given, that is 2 mole. So just I'm going to substitute the values. 3R/2 remaining 300 to 600, that makes 300 for delta T. The 2 will get cancelled out. So 3 into 8.314 into 300. So answer you will get 7,482.6 joules. Okay, please note down this formula. CP, CV they won't ask deeper level, but formulas are important. It will be just a substitution type. Don't be worried about that. Delta U, which is equal to N, that is number of moles, CV delta T. And here I want to tell you another formula, Cp minus Cv, which is equal to R. This was asked in one of those previous year JEE Main paper. A process has delta S 100 joule per Kelvin, and delta G, that is minus 10 kilojoules at 300 Kelvin. Calculate delta H. So this, hope you can do this easily. They are asking for delta H. Given delta S and delta G values. So we know the formula, delta G is equal to delta H minus T delta S. So delta H becomes delta G plus T delta S. So just substitute the values, minus 10 kilojoules. So you will be substituting it as minus 10 into 1000 plus temperature 300 and delta S is given 100. So it will become 10,000 plus 300 into 100 becomes 30,000. Minus 10,000 plus 30,000, which will be 20,000 joules or 20 kilojoules. Clear? Next question is, calculate the maximum work that can be obtained from a heat engine operating between 400 Kelvin and 300 Kelvin if the heat observed at higher temperature at 1000 joules. Once again, it is from maximum capacity, maximum efficiency. Eta 1 minus T2 minus T2 by T1. Eta value, we have to find the maximum work. Just substitute the values between 400 to 300, so which will become 0.25. Heat observed at higher temperature is 1000 joules. So we solved this kind of problem before also. The maximum work will become eta into Q. Eta is 0.25 into 1000, that becomes 250 joules. This question is asked in JEE Advanced 2020. For an ideal gas, calculate the work done during isothermal compression from 4 liter to 1 liter at 300 Kelvin. Given that 2 moles. So for isothermal compression, work done minus nRT ln V2 by V1. Thus substitute the values. V1, V2 they have given, and N value they have provided. Just work on it and tell me the answer in the comments. And the last question of today, that is, calculate the entropy change when 1 mole of ice at 0 degree melts to water at 0 degrees Celsius. There is no heat change, it's just 0 degree. So what is the entropy change? They are asking for delta S. So delta S equal to delta H of fusion by T. Similar to this question, we had another question, delta H vaporization. There the temperature was okay. They are just asking for delta H value from the given data. So we just put delta H vaporization value, but here they are asking for entropy. So you have to work upon it. Delta S becomes 0.1 kilojoule divided by the temperature, that is 0 degree, so it will become 273 Kelvin. So in total, that is 22.0, around I just took 22 joule per Kelvin per mole. That is our entropy. So do as many problems as you can. Please make sure that you are covering all those formulas in the form of questions as well. If you have any doubt in any concepts, please do let us know. We'll create a video out of this and solve the 14th question and let me know the answer in the comment section. Please stay tuned for our next session on this crash course series. Until then, practice more, because practice makes a man perfect. Thank you.